Okay, question 3. Vibrating spring has an external force moving in a straight line. The displacement is modelled by this, and we've got to use a transformation to get to this. Okay, so the first thing is we've got x equals tv, and we look at our answer. So we want v and t, and we don't want any more dx dt's. So we need to try and eliminate dx dt, and I can get a dx dt from this. So if I differentiate this, I'm going to get dx dt, differentiating with respect to time, equals, now this is product rule, so it's first t, differentiate this with respect to t, which is dv dt, first differential second plus second, which is v, differential first, which is just 1. So notice what we've got now. We've got dx dt purely in terms of t and v, which is what the answer's in. So that's good. So we've got this one covered here. We're going to differentiate again to get d2x by dt squared. So this is product rule again. So first, differentiate of second with respect to t gives me d2v by dt squared, plus the second, which is dv dt, times the differential of the first, which is just 1, plus differentiate this with respect to time, which is dv dt. Now they're the same as each other, so that's the same as saying t d2v by dt squared plus 2 dv dt. Okay, so now we've got both of those, we have to show that we actually end up with this. So I'm going to substitute dx dt and the d2x dt squared into this, and actually the x as well, into there, and we should end up with that. So let's have a go. So it's t squared times t d2v by dt squared plus 2 dv dt minus 2t times this lot, t dv dt plus v, plus 2 plus t squared times tv, and that should equal t to the power of 4. Okay, so I'm going to expand that out, which is t cubed d2v by dt squared plus 2t squared dv dt minus 2t squared dv dt, which cancels, minus 2 vtv, and then plus 2tv plus t cubed v is t to the power of 4. Well, that also cancels. Now if I divide everything by t cubed, we will get d2v by dt squared plus v equals t as required. Okay, hence find the general equation for the displacement of c from O at time t seconds. So we want the solution of this. However, it wants the displacement, so we are going to have to do our work with the general equation, but also use the x equals tv to substitute back in again, because this was just a transformation. So let's solve this. So if we're solving this, we're going to get the complementary function m squared plus 1 is 0, and therefore m squared is minus 1, so m is plus or minus I. And if m is plus or minus I, the solution in terms of v and t will be v equals a cos t plus b sine t. However, we need a complementary function because it equals something. So on this side, we will say, okay, we've got a t at the moment, so our choice, we will choose lambda t to be the answer. So for the particular integral, we're going to choose v equals lambda t. We're going to differentiate that and substitute this in. So dv by dt is lambda, and d2v by dt squared is therefore 0. Substituting these three things into that equation will give us 0 plus lambda t equals t, which tells me that lambda is 1. So if lambda is 1, the particular integral as v equals t, because this lambda is 1 in there. So complementary function plus particular integral, so we're going to add on the t to that. Okay, now we're not quite finished yet because this was in terms of v, but we wanted to solve the original equation, and the substitution we used was it x equals tv? So we now have to replace the substitution with x equals tv. So we don't want a v anymore, so let's divide by t. So x over t equals v, and we're going to replace that underneath this. So you get x over t equals a cos t plus b sin t plus t, and then you multiply it by t. So it's t times a cos t plus b sin t plus t. That's your general solution. Okay. Then it says, state what happens to the displacement of c as O from O as t becomes large. And as t becomes large, the a cos t can only vary between -1 and +1. This can only vary between -1 and +1. So in essence, you're just going to get a massive number times another massive number is going to get even larger. Okay, so x is going to get even larger as t gets larger. So as t gets larger, x gets larger too, it just gets bigger and bigger and bigger. And then comment on the model with reference to its long-term behaviour. Well, it's talking about a spring, and the spring can't keep getting longer. It will snap eventually. So I would say the spring can't keep getting longer. It would snap. Okay, that's question 3.